In A2, we're going to talk about how we can determine if two triangles are similar. Now, there's this angle-angle similarity theorem, which tells you that if two angles of one triangle are congruent to two angles of a second triangle, then the two triangles are similar. So the nice thing is we're looking here at this. We don't have to know that the triangles are similar to start. We can determine that they're similar. And we don't need to know that all three angles are congruent to do that. We can just know that two of the three are. So notice in this triangle, angle A here is congruent to angle D, and angle B is congruent to angle E. So we know A goes with D, B goes with E, and once we know those two are congruent, we know that the triangles are going to be similar. Just so you know, once you know that two angles are congruent, let's just assume, let's say this is 40 degrees, so this one's 40 degrees, and let's say this one is 80 degrees, and this one's also 80 degrees. Well, you know the three angles of a triangle have to add up to 180 degrees. If these two add up to 120, that means this one has to be 60 degrees. Well, same thing over here. So the thing is that once you know that two angles are the same, you know the third angle is going to be the same. And when all three angles are congruent, you know that you have similar triangles. So that's where it comes from, but we don't ever need to really find this third side to be able to know that because of this similarity theorem. It only requires that we know about two of them. So when we're determining whether triangles are similar or not similar, the easiest ones are obviously, for example, B is an easy one. Because when I look at B, I say, okay, well, this angle here is equal to that angle. This angle is equal to this one. So two angles are similar. So yes, this is similar. And I know it's similar because of the angle-angle similarity theorem. Now I start to get to a couple other ones a little bit different, like I have to kind of use a little bit more logic and I have to use a little bit more of what I've learned in the past. For example, if you notice in A, I find that these two lines are parallel. Well, if those two lines are parallel, we have to now think of these lines. For example, this line here becomes a transversal. And you know that these two angles have to be equal because corresponding angles are congruent. So if I think of it in that terms, then I know that this green line over here is also transversal, which means that this angle and this angle have to be equal. So what I've got going on here is a small triangle that is, and then I have this larger triangle, but I know that they have the two angles that are congruent. So yeah, the two pairs. So yes, these are similar. And again, it's because I was able to prove angle-angle similarity theorem. So this recalls things that I have to remember about two parallel lines and a transversal. In C, it calls to mind another skill. Now I'm looking at it, and what they're telling me that this small angle here is congruent to this angle there. Okay, so I've got one angle. Now, they're showing me that those two sides here are the same. And if I just look at this big outer triangle, right, I know that the big outer one is an isosceles triangle, which means that the base angles have to also be congruent. So if the base angles are congruent, then if I break these into their little two separate, notice that I have one angle that's congruent with one on the other one. I have this angle, which is congruent to this angle. And so now I have two angles that I've been able to prove that are congruent. And so yes, these are similar. And again, angle-angle similarity theorem. So far I've been able to prove it in A, B, and C using things I know about isosceles triangle, about parallel lines and transversals, and this one was just obvious. This was straight out AA theorem. Now here is where it gets tricky in D. We're trying to figure out in D, are these two triangles similar? Now, first of all, it's very difficult to see what they're talking about, but what they're trying to figure out is this small triangle similar to this larger triangle here, okay? Now here, yes, I know that this angle is equal to this one. That's easy. And then I also notice that this little angle is the same angle for both triangles. And so yes, these two triangles are going to end up being similar because they have the blue angle here is similar to this blue angle, and the red angle is, angle 2, is the same for both triangles, which means it only leaves one more angle over here, this angle here with this angle here. And so yes, this one is also similar. So as far as I can see it, all 4 of these angles are similar because we're able to prove it through the angle-angle similarity theorem all 4 times. Obviously, some required some other strategies and really thinking a little bit more outside the box, and B and D might have been more straightforward. Using angle-angle similarity, we're now going to use proportional math to find missing values. We know these triangles are proportional. We did one similar in the previous slide. We know that if these two lines are parallel, we know that these angles are congruent because of corresponding angles. We know this angle and this angle are also congruent for the same reason, and therefore we know that our two triangles are similar. And by two triangles, we're talking about this smaller internal black triangle, and then we're talking about the larger green triangle on the outside. And so we're able to use proportions. We know that the smaller triangle, really in essence, right, the smaller triangle is 3 and 5, and this is the parallel part, right? And the green triangle is 3 plus 1, or 4, and this is 5 plus x is the whole side, correct? So if I'm trying to do proportional math, I know the sides that go together. I know, for example, that 3 goes with the 3 plus 1 side, so I know 3 over 4 is going to be the relationship of the left sides of those triangles, and then I know that, for example, this part here, the 5, is going to correspond with, on the larger triangle, with the 5 plus x. So 3 over 4 is going to have the same proportion as 5 over 5 plus x. And so again, I can use proportional math again to solve this problem. It's going to be 3 times 5 plus x is going to equal 4 times 5. I have to remember to distribute the 3, so 15 plus 3x equals 20. I'll subtract 15 from both sides. I'll get 3x equals 5, and I'll divide by 3, and I'll get that x equals 5/3, or 1 2/3. So that's the length of x. And so that's how I find x. So again, I just set up my proportions. For example, again, like we did here, the left side of the small triangle over the left side of the large triangle, which the large triangle would be the 3 plus 1. Here they want me to come up with the similarity statement. So first I have to prove that the triangles are similar, write a similarity statement, and then they want me to identify different pieces. So let's just go kind of in order. Let's look at the scenario we've got. Notice again we have these two parallel lines. Once I know those lines are parallel, then I'm able to, again, assuming this is a transversal, I know that angle C and angle D are corresponding and congruent, so C is going to go with D. I know on the other side of this, I know angle A is going to equal angle E, because again, corresponding parts, so A goes with E. And so then again, I know that angle B is going to match with angle B. So basically, I've got ABC is similar to EBD. Yes, I got angle similarity tells me they're similar, and that's the order that I need to write the letters, because again, I know A goes with E, A and E, right? And so again, order of that matters, okay? Then I come here and I have to try to find the length of Y. Well, first I have to figure out scale factors, okay? So what happens here is I know that, let's do this side here, I know that BD, right, is going to go with or correspond to BC, right? Notice our triangles, BC and BD go together. So I know I'm going to get my scale factor from that. I know that BD, this is a little bit messy, sorry about that. I know that BD is 4, and I know that BC is 7. So I know my scale factor from, let's say, the small into the big one or whatever, small over big is going to be 4/7. So I know I'm going to use that scale factor to find the rest of my pieces. So for example, when it comes to BE, I know that 4/7 is going to be the same scale factor as BE, the small right side there, over the whole thing, which is 3 plus x. So again, I'll use proportional math. 7 times 3 equals 4 times 3 plus x. 21 equals 12 plus 4x minus 12, right? I'm going to get 4x equals 9, and divide by 4, and I'm going to get that x equals 9/4, or x equals 2 1/4. And so I got x. Using that same relationship, right? Again, here it's at a BE over BA. That was BE over BA. Is just this part here. That's BE over BA. And that's what led me to this whole part here. And then Y, and again, I know that Y is going to have the same scale factor as everything else. It's the base is going to have the scale factor, the base of the small to the base of the large. So again, I'm going to do, I know the scale factor is 4/7, and I know that that is going to be the same as Y/8. So again, I do 7Y equals 8 times 4. 7y equals 32, and if I divide both sides by 7, I get y equals 32/7, or 4 4/7. So I'm sorry that all our examples seem to have fractions, and so I'm able to find all the missing pieces or parts here using, again, the scale factor. It just takes one relationship that you set a scale factor for. In this case, we did BD over BC, and it just helped us find everything. So here they want us to prove that triangle AOC, which is basically this left triangle, they want us to prove that this left triangle is similar to the right triangle, or the triangle on the right, which is BOD. So the first thing we're going to have to do is we're going to have to prove, for example, that we have a couple of what the angles are. We're going to have to try to figure out angles that might be congruent using angle similarity and stuff like that. So I can tell you right now, even if I'm not going to write this as a formal proof, I can tell you in step 1, I know that angle AOC equals angle BOD because vertical angles are equal. So AOC is congruent to angle BOD, and the reason would be vertical angles are congruent. So I already proved that one set of angles is equal, right? So then I got one pair of equal angles. Then I say, okay, well, what else can I prove? Well, they tell me that these two lines are parallel. Well, once I know that these two lines are parallel, I know, for example, that let's say I know that this line right here is a transversal. And if that line's a transversal, this angle and this angle are alternate interior angles. And I know then angle C is congruent to angle D, right? Because alternate interior angles are congruent. So I now have two angles that are similar. I don't even have to keep going, but I could do a third one, right? Even though it's not necessary, because again, I know that this would be another transversal, and this angle here would be alternate interior to this one. So I know angle A has to be congruent to angle B for the same reason. Both of them are the same reason. So I've already proven here that I have three congruent angles, which means definitely these triangles are similar. I only needed two. So I know, and again, the corresponding parts, A goes with B. So triangle A, triangle B. I know O goes with O, and I know C goes with D. And I know that these triangles have to be similar because of angle-angle similarity theorem. And so we're able to prove it. Like I said, this one was not necessary. It's not needed, although it is true because we only had to prove two angles, and we already proved those. And the last type of question is really common, and I love doing it because it's a way of solving word problems that are very common on standardized testing using proportional math. So you've got this flagpole, right? And the flagpole casts a 50-foot shadow. So here we have our pole, right? And it casts a 50-foot shadow. So here's our shadow. It doesn't tell us how high our flagpole is. It says at the same time, and the same time matters because, again, the reason it's the same time is just to show you that the sun didn't move, so the shadow will be in the same spot. So here we have a woman. She's pretty tall, right? And the woman casts, again, a 40-foot shadow. Now, the nice thing is that we were given the woman's height. The woman is 5 feet 4 inches. So now it says, how tall is the flagpole to the nearest foot? Well, we can create a proportion. We can say, for example, the height of the flagpole over the shadow on the left is going to equal the woman's height over the shadow on the right. Now here, everything is in feet, and we do have this 4 inches, so we are going to have to convert 5 feet 4 inches to just feet. So how I do it, or one way to do it, is we know that 5 feet 4 inches is 4 out of 12 feet, right? And if I kind of do that, it would be 5 and 4/12 as a decimal would be a third, or 0.33. So instead of 5 4 inches, I'm going to do 5.33 as my numerator. That's going to be better to do that. The other way I could do it is convert everything to inches, but I don't think I want to do that. So when I do my math, I'm going to do 40 times x equals 50 times 5.33. So I got 40x equals 266.5, and I'm going to divide both sides by 40. And I'm going to get that x equals 6.66 feet, or 6 2/3 feet. And 2/3, I know, is 6 feet 8 inches. And so, again, I know my flagpole, my flagpole should be 6 feet 8 inches. Now that doesn't seem very high for a flagpole, but that is the answer. I'm going to double check the math, but I think that is correct. And yeah, the numbers are right. So just make sure that you set your proportions up correctly. And if you put, the flagpole on top and the shadow on the bottom, that you do the same thing when you're doing the one you're comparing it to. And you also want to make sure that you're all completely in the same units. All feet, all inches, all whatever.